Hello, this is Bill Foote, and we're doing Bayesian-oriented business analytics. I want to spend a few minutes talking about the core approach that we use, and it's information theory. It comes from a theory of communication by Claude Shannon, building on Hartley, building on others, called entropy in physics, and digital or information entropy is going to be our approach for measuring uncertainty. And to illustrate a lot of aspects of this, but just try to break it down and get into something very, very similar. I do have some notes available associated with this video. We're going to define information as the amount of uncertainty that's been removed, resolved, made systematic. And here's the key word: when we learn an outcome, when the future that might happen happens. Okay, we're gonna take a very simplistic way of looking at this in order to get at the groundwork associated with information we deal with in analytics, which could be text information, very unstructured, could be very structured databases, could be numerical, could be logical, could be symbols of various types. Uncertainty, on the other hand, there's several very interesting definitions here, and whatever uncertainty means. The one I tend to use is from Nicholas Cusanus, medieval philosopher, theologian, mathematician, and they did kind of everything in those days. I think he also built clocks because he wanted to compute something. And it's what we don't know what we don't know. I think a former Secretary of Defense hijacked this definition without attribution. Anyways, let's start with a simple example. Our problem is very straightforward and very difficult. We want to compare two different models. We want to know which one is more informative than the other. And when it's more informative, we will therefore say it is more consistent with the data. Well, here's the data. It comes from competition between the Fordham Rams and the Manhattan College Jaspers. It's a 100-year rivalry or so. You can read all about it at both of their college and university websites. And, well, they have rivaled in just about everything, and so they decide, well, here's one thing that we haven't done yet. We're going to create two teams. Jill is going to be the Fordham Ram, who will run the Fordham team, and Will be the Jasper, after brother Jasper, baseball team stuff, for the Manhattan Jaspers teams. And they're going to forecast, make a 5-day forecast of rain or shine. There are very strict rules about what is rainy, what is shiny, cloudy, how does that, okay, I'm not even going to get into those. It's on or off binary. Okay. The actual observations ended up being 2 days of, and by the way, these can happen on any given days because everything in this little model is highly independent. Not true of the weather, though, anyways. 2 days it rains, 3 days it's shine. Oh, we forgot the face there. It's probably a slightly cloudy day there. Jill, the Ram team leader, they forecast 100% rain for 2 days and 60% rain for each of 3 days. Will, the Jasper leader, says it's always sunny in the Bronx, so 0% chance of rain straight across. Now, there's a couple of ways we could look at this. One is called the hit rate. I'm going to use the physicist notation just because it's compact, in between two pointed brackets, less than or greater than bracket. That'll be the average. Now, the average here is Jill twice chose a 1, 100%, and 3 times shows, well, she said it was 60% chance of rain. It actually was the opposite of that. 1 minus 60% is 40%. So actually, what we need to compare it with is 40%. 3 times 40. Add this up for 3.2 hits in 5 days. So this is the hit rate. We often use this. It's one of the easier things we can kind of play with. But it's a forecast of the future that unfolds as more and more uncertainty is revealed. For example, we could do it from here and then add this, and then add this, and then add this, and get different hit rates on different days. Which, if they're doing the box scores and betting on this, which of course you know they probably are, certainly toothpicks in the dining halls, how many do you accumulate? They might be doing that, and that's an updating scheme. Look at Will. His average is 2 times 0, but 100% for each one of these. Remember, this is 100%, 0% rain, 100% sunny. So he gets 3 hits. And the judges say, well, within our rules, it's pretty even. So the hits, keep on coming here. We can't discriminate between the two. So I guess we're going to have to give them, there's a prize check of $1,000, so each get 500. Okay. That's one way of doing it. Okay. Now here is another way. And this is a more interesting way. And I first learned about this way many years ago in a set of discussions. It's basically the decision frame that Arnold Zellner uses. Howard Rafa used it out of Harvard. And he's the frequentist turncoat into Bayesian analyst, decision theory. And it's the umbrella problem. Daniela Navarro uses it in her Libra text. Okay, it's a very, very popular approach. Weather, we all know the weather, and we know how to hedge. And the gallows humor in the Bronx is carry an umbrella, it won't rain. Okay? And it's worth it. Well, what is it worth? Well, we're going to use something called grief. Information lost is what this is going to end up being. Grief to carry an umbrella is -1 on an index. It's less grief to carry an umbrella than if you're caught in the rain. More grief if you're caught in the rain. Okay, could be the hours of standing in front of the open hearth and getting your clothing. You can come up with whatever metric you want to use, but the point is one is lower than the other, and 5 times higher, more grief if caught in the rain. Okay? Imagine you're in a suit of clothes, going off to an interview. You say, always sunny in the Bronx, and you get soaked to the bone. No umbrella. Remember, it's nice driving rain down. It's not going to, maybe the bottom of your trousers or shoes, but it's a lot of grief sitting there in an interview, soaking wet. Okay, that's the kind of grief we're talking about. And if we apply this, well, look at how this works. The grief is applied by multiplying the grief number times the forecast. Very simple. -1 times 1, -1 times 1, -1 times 0.6, -1.6, -1.6 for Jill. Okay, I mean that makes some sense. They forecasted that, and now they're working as if Jill is working as if her forecast is true. They call that skin in the game somewhere, and but she hedges it. Even on the day that she is absolutely sure, the first 2 days, absolutely sure there is going to be rain. Will, on the other hand, gets wet twice. Afterwards, no problem. Okay? But the grief is all concentrated. Okay? Didn't get the job, by the way. So after the interview, uh, soaking wet. Will, so we can now compute the average grief rate, or the average, if you will, information left out. Okay, the average hole in the, their forecast. All right, here it's a -1. We might call it a bit or a RIT for a rain information, rain digital bit, digit. All right, so we could do that, but let's calculate what ends up being the average across these lost bits. And here we get 2 times -1 plus 3 times 0.6 times -1. Okay, and they add up to -3.8 grief points. And we're going to call this uncertainty, basically. And here's will twice, soaking wet, -5. The rest of the time, 3 times 0. That ends up to 10. Much more unpredictable is how we're going to interpret this. Jill, with the umbrella, made her life more predictable. We're going to call this more predictable. We're going to call this less predictable. Fred James at CERN and also at the, I think there were lectures as well at the Fermi National Accelerator Laboratory. I happened to attend those in the early 2000s, years ago, and I saw, oh my God, there's the umbrella again. So you can check this out. I think that's CL2K. That's a 2. FNAL.gov conferences. That's on the System Dynamics website. Okay. So there's yet another way of thinking about this. And although that's pretty good, this one's going to give rise to the use of a logarithm to help with this, because logarithms basically add up the grief as opposed to multiplication. So multiplication is kind of compress it. Logarithms expand it in an addition. So I'm unhappy, plus I'm more unhappy, plus I'm more unhappy in the logarithmic sense. And it also lines up with system uncertainty. Add more complexity, it's an additive problem. And you can read all about it in Shannon and other places. Claude Shannon in 1948. Okay, I don't think Nicholas Cusanos had anything to say about this. Okay, and we're going to call anything logarithmic, we're going to call it a score. Okay, now what are we scoring? We're going to score probabilities in this particular case. Now, we've already done this if you've seen previous videos of Bayesian approaches. Bayesian approaches computes a likelihood, but if we were to take the logarithm of that likelihood, that would be very interesting. And there's a problem with doing that because it can't be, the probability always has to be positive, but if it approaches 0, the computational system can't handle a really, like 10 to the 132nd probability because it's too close to 0 for the system, and it'll come up with not a number error in R and in other systems as well. So we got some work to do here numerically, but let's get back to Jill and Will. She's right here, wrong here, right here. That's an interesting binary approach immediately. The probability, since these are percentages, the probability is 1 times 1 These are all both and. Both this and this and this and this and this means a probability rule that is multiplicative again. And we can say that's 1 squared times zero point 0.4 cubed, or 0.0464. And same for Will. Will is zeroed out, so he's easy, all right? And you can see that the score is going to be here, but the log score will be very interesting as we do this. So if we were to take log scores of these, we would find that Will is, and I change it to 0.0001 because if we take the logarithm of 0, we get because it approaches, logarithm approaches 0. It never hits 0. The logarithm actually is a series, a power series, something called a power series. I have another little video on that. But what I want to do in just the next minute or two is use this idea of computing the joint probability of counting the ways, the sequence of rain and how rain and shine, it's all commutative. It doesn't matter here. We're purposely making it non-commutative. And because she has a higher likelihood, the Rams have a higher likelihood, they lose less bits. Well, that's like minus 10 over here. The minus 3.8. Okay, so the log score lines up with that very nicely. But it's also additive. And because it's additive, we can add uncertainties together to get an average uncertainty. And that's where we are going to go. We've already got that almost done here, given that these are all probabilities. And again, if you multiply this times a hypothesis that the Rams will win versus, let's say, 75% of the time, and the Jaspers won't, because we know forever they've been bad rain forecasters. They don't seem to care about that. It doesn't matter. They never had a astronomical observatory on their campus. The Fordham Rammers have. They also have a seismic station there too, which is very interesting. Be a geophysicist at Fordham, I guess. But we could get into that. But the point is, with all of that jabber, is we see a tremendous difference. And again, this minus sign to me is loss. Now, if you multiply this times minus 1, you get 9.21 logarithmic bits versus 2.7974 logarithmic bits of what we're going to call the amount of uncertainty. And uncertainty will be the average of all those pieces of information. Removed, resolved, made systematic when we learn an outcome. Okay, so let's drop down a little bit and spend just a couple of minutes with a measure that people have been using, a logarithmic measure that people have been using. So if we think those logs work, I go into lots of pain and Sturm and stress about this here. But suppose we have two forecasts. One says it's not going to rain very often, it's going to be mostly sunny. And the other says it's going to rain a little bit more often and a little bit less sunny. Okay, so it's a little different than the RAM forecast. I mean, we could do some notion of 2 out of 5, 0 out of 5, yeah, but let's play with this for a moment, okay? In any case, it's binary. Okay? And we're going to define a measure called H, probably after Hartley in 1928, Bell Journal. came up with. So we're gonna honor him with an H for what Claude Shannon calls information entropy. Here's the formula: minus the sum of a probability like 1/8 times its log. So we're basically looking at the log, what might happen here. And I can go into it in a lot more detail, but it's the idea of a log of 1 versus 8, 7 versus 8. It's like a log, it's like a ratio of not odds, but ways in which rain can occur out of 8 ways, 7 ways out of 8 ways, 1 way out of 4 ways, 3 ways out of 4 ways. Like came back to counting the ways, but putting it in logarithmic scale allows us to dimensionalize this. Now, there's a very useful logarithmic scale that most everybody is really familiar with. Uh, gosh, that's the decibel. That's a logarithmic scale. Sound, it's not an intensity scale like temperature. Sound can get much louder, but if you add more tones to it or uncertain tones, okay, put a message together of A and B. Okay, you can go AA, AB, AC. That's it. It's highly extensive. Okay, I can go AAA, ABA, ABC, BA. I can do all of those combinations, but they don't get any louder. Okay, they just get longer. That's extensive. Intensive means they get, okay, I add more heat, I'm going to get hotter. I mean, it gets more intense. Okay, and I get more intense trying to avoid it. Okay, so keeping an extensive versus an intensive, and gosh, I think I learned that in high school physics. We were talking about this issue of thermodynamics, entropy, okay, which we're applying to uncertainty here. So this is extensive. So 1 out of 8, 7 out of 8, and when we do this, we get, here is the average, here's the expected uncertainty with rain. It's like losing 0.26. Now we're using natural logarithms. The natural exponent is also a series, an approximation. It's not an actual number per se in our systems. Somebody loads it in and they got to ask, well, how many digits did you use? Well, I don't know. I use 20, 30, 40, 50, 132, whatever the number is. And but you get a close enough number. I said, that's fine. That's fine. Just realize that we don't really know what it is. That's why it's called a transcendental number, by the way. You always have to keep transcending. And so this is like losing 0.26 bits. This is like the 7/8, like 0.12 bits. Now, 7/8 means it's more predictable. 1/8 means it's less predictable. Same down here with 1/4 and 3/4. More predictable, 3/4, less predictable, 1/4. And their bits that are lost ought to reflect that. That's called a monotonic property. They should reflect that, and they do. Now notice we put a negative out of it so that we could just use positive indices here. This is a scoring of how much blindness is inside of this. We cannot see the future, but we also can't hear it, we can't touch it, we can't sense it in general. But we can think about it, and these are thoughts. And it led to Joseph D. Finetti, the actuarial crowd, to say, well, these things don't really exist. What they do is they represent a mindset about what might exist. And I think that's very much good epistemology with a couple of other things added to it. And we're trying to give it a logical foundation in this case, simple rational numbers. And that's what we've done here. Okay, so all of this works. And it should follow the intuition that this setup with 1/8 and 7/8, notice I didn't tell you the number of times it would rain or the number of times it would shine. I didn't need that. And that's the beauty of this. Information entropy does not depend upon the actual outcomes, it depends upon the information structure, and that includes this, the probabilities. How often we think something is going to happen in the future. How often, not what actually happens. And so we get 0.58 for the bottom one. Well, it looks more, it's a little bit closer. The 1/4 and is bigger than the 1/8. The 3/4 takes a little bit out of it. Okay, it's, even though this is very, 1/12 here, very predictable, this is much more unpredictable. And this, the predictability of this, which is 0.22 over here, versus 0.36, when they average out, okay, we get something even less predictable. This one here is very predictable because of the 7 versus 1. This one less predictable because of the 3 versus 1 in 4 ways. Okay, so the uncertainty, B, is more surprising than A. You know, we have this to bank on. It's funny. This is what the Fordham Rams kind of said too, but they actually went against the Manhattan Jaspers tremendously. This is what Manhattan Jaspers are thinking. So, okay, some ideas here. This is going to be our way to measure uncertainty in information. I made some more discussion notes, which really don't help us too much here. And also in these discussion notes is an algebraic geometry. Now, algebraic geometry is very, very important to machine learning and statistical learning in general. And it's all Bayesian. All of that's Bayesian. And what I want to do is kind of, let's see if I can't. The logarithm is actually a power series in the log of x is x minus 1 minus 1/2 x minus 1 squared. I can bring all of this theory down into a very practical calculus. No infinitesimals allowed here. Very simple calculus of an algebraic geometrically simple calculus of polynomials. Because what happens is this is going to be the shape of our uncertainty between 0 and 1. That should be a 1 right here. Between 0 and 1, probability of 0 versus a probability of 1. Okay, we have two choices, rain or shine, 1/8, 7/8, etc. The uncertainty ought to be 0 at either end, because we either know absolutely nothing, we don't care. Okay, the 0 probability of happening, that's certain. Or there's 100% probability of something happening, that's certain. It's either going to be rain or shine. And when you're at either end of the spectrum, you're acting as if you're certain. But somewhere in the middle, and notice this thing is going to be symmetric, this way of thinking, and it's going to have a maximum right in the middle, right where it's 50-50, and that makes sense. That's the most uncertain. We just don't know which way it will go. 0-0, yeah, and the 0-1, yeah, we know it's going to be raining. How do you know? I have got inside knowledge. Or it's not going to rain, it's going to shine. I've got inside knowledge. Okay, you're certain. But this thing here, this is flipping a coin. That's the most uncertain, unpredictable situation. I work all this through. Anybody would like to talk about it, please let me know. It relies on a very simple algebraic trick from Lagrange in a Taylor expansion of a simple polynomial, which you can express just so many things this way, but especially our very special logarithms and exponentials as operators. We can express them as, in this case, second degree polynomials. And then it's high school algebra. I mean, high school algebra probably learned in sophomore year, maybe, and some of us for freshman year, all right? And for others even earlier. Um, but it comes up with some unsurprising but very interesting results. Okay? So anybody who wants to see that can, and can also read about it. And I'll trounce through that a little bit in another video. So we've got about a half hour here. That's enough. This is Bill Foote, and this is a very short introduction to uncertainty with a couple of practical examples and a pointer to the future. Analysts, data analysts need to know these kinds of foundations at this basal level. Minute 31, we're done. Thank you very much for your kind attention. I'll let you go back to whatever it was you were doing, hopefully a little bit more certain than you were before. And again, encourage each other daily while it is still today. So much more to learn. Can't wait to get to the next stop on this journey. Take care and thanks.